So welcome everybody. Let me share the screen. That's okay. And I will show the schedule for today. Yes, that's good. Welcome to the multidisciplinary section, where we are entertaining a number of interesting topics here in this session and in a following session. On behalf of everyone, welcome, and let me acknowledge the unceded territories of the indigenous peoples that we are all tuning in from. My source water is Mi'kmaq, so that I'm tuning in from the eastern side of the continent. We have a number of speakers who are also emphasizing the water cycle, and so I think we'll just go ahead and start with Vanessa Foord. If you would like to, I'll stop sharing and I'll give you a heads up in about 10 minutes, if that's okay.
Yep, sounds good. Just get my presentation up here. Just confirming that you're seeing that and hearing me okay?
Yeah, that's great. Thanks.
Thanks. Thanks for introducing the session. I'm Vanessa Foord. I'm a research climatologist with the British Columbia Ministry of Forests. I'm going to talk about using weather and microclimate measurements to assess wildfire risk in different stand types. And just want to acknowledge my colleagues, Rulan Zayo, Philip Burton, Joseph Shea, all from the University of Northern British Columbia, as well as Rebecca Bowler, also from the BC Ministry of Forests. So the rationale for this work happened because of significant wildfires that we had in the central interior of British Columbia in 2017 and 2018, where it was noticed something called wildfire skips, where there was juvenile forests that were burned less severely or not at all, as shown in that satellite image. You're probably easy to pick up that nice dark green locations in the middle. That's juvenile pine plantations that were not burned. And then on the outskirts, you can see a lot of fire scars and burned trees in older mature forests. This was counter to the understanding that generally older forests are less susceptible to high intensity wildfires, and that sparked several research projects to investigate. This work is part of a larger research project led by the University of Northern British Columbia on estimating fuel moisture content in different stand types, whereas my portion of the project is to understand, are there microclimate differences that would affect the fire weather variables to cause the juvenile pine plantations to be less risky than the older stands. So we have 6 field-based sites to look at this problem. 3 of the sites are around the community of Smithers, which is in the northwest central part of the province, and then also 3 around Prince George, which is pretty close to the middle of the province of British Columbia. So showing the sites here on the satellite images, as well as the nearest British Columbia Wildfire Service weather station that we use to compare our field data to. So here's what the study design looks like. I'll move from left to right in terms of the pictures. So we have, an approach where we're directly comparing weather and microclimate conditions in an open stand. The open stand is regenerating clear cut, where there's small trees growing, shrubs, and a lot of slash left over from the harvesting, as well as a nearby juvenile stand. This is planted lodgepole pine of about 20 to 30 years old, and is fairly densely or closely planted together. And then a nearby mature stand, so unharvested primary old forest of at least 80 or 100 years plus, Not as dense as the juvenile stands. Old forest dynamics tend to be pretty patchy in terms of openness. And for all 6 locations with 3 of these subplots, they're all within the subboreal spruce ecological zone of the province. So the forest types are very similar. So here is the microclimate and weather monitoring equipment that we're using. In the open sites, we have full weather stations. 4 of the 6 sites are onset Hobo U30 data loggers that are solar paneled, where we're measuring temperature and relative humidity, both at 2 meters and 30 centimeters. We're also measuring surface temperature, wind speed and direction at 3 meters, rain, solar radiation, barometric pressure, soil temperature at 15 centimeters depth, and soil moisture at 5, 15, and 30 centimeters depth. Moving from left to right in the pictures, showing the next picture is an example of some of the in-stand monitoring, where we have these smaller onset Hobo micro data loggers attached to our soil sensors, the same as the weather station set up in the opening. So we're measuring soil temperature at 15 centimeters and then soil moisture at 5, 15, and 30 centimeters at all the different stand types. And then that picture is also showing an example of an internal external temperature sensor 30 centimeters above the ground that we use to measure surface temperature. The third picture is UNBC supplied weather stations, Campbell Scientific based weather stations based on a CR300 logger, and using an all-weather sensor for 2 of the 6 stations. That fourth picture is another in-stand picture of our rain bucket, as well as some of the 30 centimeter temperature and relative humidity measurements. And then lastly, the final picture is showing a Davis wind speed and direction smart sensor coupled with an onset micro data logger. The wind speed and direction measurements in stand are also made at 3 meters, just like in our open locations. We're not measuring snow in this study. Snow is really quite difficult to measure directly with sensors. However, we do run the equipment year round, and we can tell things like the start of the snow season, the end of the snow season, and the timing of melts with the data that we leave running. And that's really important for starting the fire weather index codes. Here's just an example of what the stands look like overhead. These are fisheye photos, or some folks call them canopy photos. Obviously, the open stand is fully exposed. The juvenile pine plantation is in the middle. You can see that it has a lower canopy cover compared to the picture on the right, which is the mature stand, where there's lots of shading and the canopy is pretty tall. However, the difference between the juvenile and the mature stand is that the mature stand has a lot of open patches lower in the canopy. Hopefully you can see some of the light poking in at lower heights. However, in the juvenile stand, because those pine trees are pretty densely packed, there's less light getting in the sides of the stand. So just quickly, I'll go through some of the different climate variables that we've measured directly. We started the measurements in June of 2021. So in some of the sites, we did capture some of the effects of the heat dome, which was kind of cool. So temperature is being shown on the left here in the open, juvenile, and mature stands. And generally what we see as expected, the open is the warmest. However, the mature and juvenile are relatively close together. And with relative humidity, again, the relative humidity is the lowest in the open stands, and between the mature and the juvenile stands, they're pretty close. However, the juvenile stand does get a little bit drier than the mature stand. Wind speed is an important fire weather index variable. So wind speed's on the left here. Of course, the open is a lot windier, both in average and maximum wind speeds. And then when we look at the difference between the juvenile and the mature, with maximum wind speeds, the juvenile is greater than the mature, but with average wind speeds, it's actually the mature that's greater than the juvenile. With rainfall, as you can probably imagine, in a topographically complex place like British Columbia, the rainfall between all these sites is highly variable. So I don't have too much to say about that other than it's a useful variable for understanding the melt season, which is that orange line that peaks above 100 millimeters in April, where we can see the snow, the timing of the snow melt. Surface temperature, we only have 2 years of data for so far because we added it late in response to comments from Natural Resource Canada wildfire experts that surface temperature is a very important variable. In general, we see the surface temperature varies the most in the open, and there's quite large differences between the maximum surface temperatures and the stand types. So the open area can get above 30 degrees, whereas the juvenile stand gets close to 30 degrees, but doesn't seem to cross it. But the mature stand gets below 20 degrees. So quite a large temperature difference between the juvenile and mature stands during the hot periods, which could be important for wildfire risk. Surface temperature is also a good indicator of snow season timing, where you can see it flat lines in the winter there because these sensors are covered in snow.
That's 11 minutes.
Great, thanks. Soil temperature is the variable on the right there at 15 centimeters depth. It's a great indicator of when the sites start to green up and the vegetation is flushing. And generally we see soil temperature is warmest in the open and coolest in the juvenile. And the last variable is soil moisture, which is pretty complicated to understand. Basically, we see that the juvenile soil moisture fluctuates the least, as it doesn't recharge most with rainfall, but it doesn't lose a lot when it's really dry. And unfortunately, our mature sites are quite prone to animal damage, but we've created a cage system to protect some of our cables there, which we hope to improve our measurements for upcoming years. And so just in my last couple of slides, I'll show how we use those variables to calculate wildfire risk. Vapor pressure deficit is shown on the left there. Vapor pressure deficit can be a good indicator of wildfire risk. And also high vapor pressure deficit can limit tree growth. So when the vapor pressure deficit is high, the trees are potentially transpiring water, but also they could be stressed and have shut down their stomata and are not transpiring. And generally we see that the vapor pressure deficit is higher in the mature stands as opposed to the juvenile, which is interesting. And then when we look at different drought codes on the right, fine field moisture code on the top, duff moisture code in the middle, and drought code on the bottom, which kind of follow from surface to a little bit deeper between these different drought codes. Generally, we find the drought codes are higher in the open, of course, and between the mature versus the juvenile, they are higher in the mature than the juvenile generally. And also the timing of the snow season is really important to running these drought codes when we compare it to a wildfire service weather station, which is the orange line on the right graphs, and our weather station in the open and the blue. When we start the timing of the fire weather codes at the end of the snow season, which we can tell from our data, we end up generating a much higher drought code throughout the season, kind of as expected, but this was a lot more reflective of the severe wildfire season that we did experience in BC in 2023. So this is just my last data slide. The graph on the left is showing how many times these fire risk thresholds were broken in 2023, where we did have a lot of wildfires occurring across the province. So definitely the wildfire index variables are working well in terms of indicating wildfire risk. And the graphs on the right are comparing some of our in-stand measurements to BC wildfire station data, where generally we see with our field-based measurements, our drought codes are higher, but it actually ends up that some of the fire risk variables are actually lower because our wind speeds are being monitored at 3 meters as opposed to 10 meters in the wildfire weather stations, and that makes a big difference to the wildfire risk. But 3 meters is a bit closer to the ground and potentially are giving us different indications. So we've only had 2 fire seasons. One was really wet and one was really dry. So we're continuing to monitor and we plan to do more statistical analysis as we gather more data, compare our data with field collected fuel moisture, and also compare with remote sensing of wildfire risk. That's it. Thank you.
Great. Thanks, Vanessa. Are there, I don't see any questions in the chat, I think. Let me just go back there. Either the chat or Q&A are fine for posing questions for the community, for the participants today. I guess you had addressed the question that I had about the maturity of the stands and the mean or the max wind use in the fire. So can you specify which? Is it mean or max that you emphasize in fire risk in general, and how would you accommodate the height of the trees versus the height that you're measuring?
Yeah, so I did mention that, yeah, in the graphs, we showed both mean and max wind speed when we're looking at the comparisons between the juvenile and mature stands. So the mean wind speed was greater in the mature stands than the juvenile, but the max was greater in the juvenile than the mature. I think the way the fire weather variables are calculated is they take the wind speeds that are occurring at 12 o'clock, so kind of midday, to calculate those variables. And then I was just trying to explain that the difference between some of the fire weather indexes that are related to wind speed are quite different between our weather station calculations and the BC Wildfire Service, because they measure wind speed at 10 meters, whereas we're measuring at 3.
Okay, thanks. Very good then. I think we should move on so thanks, Vanessa. To Victor Peñaranda-Vélez, tuning in from Mexico and talking about downscaling extreme events in that area. So Victor, can you share your screen?
Hi. Okay, my screen is, I think is, okay. Good.
Perfect. Okay, thanks.
Okay, I'm gonna start. Hello, everyone. I'm very pleased to be here today. Today I'm going to present some research results that my colleagues and I were working on for a while. I expect that this presentation invite you to get any interest in understanding some different kind of models for modeling precipitations. Okay, the agenda for today starts with some motivations that conduct the development of an innovative approach to downscale coarse-scale precipitation products over the complex terrain region of Mexico. At the end, some final comments will wrap up this presentation. Let me start this presentation recalling a thought of Dr. Mandelbrot. Nature exhibits not simply a higher degree, but an altogether different level of complexity. This thought reminds me that precipitation has been considered as one of the most difficult atmospheric phenomena to be described and modeled. This is so because of the higher complexity of its patterns. Going along with Dr. Mandelbrot, the nature of precipitation patterns belongs to a different level of complexity, and we think the fractal theory could help us to solve some of its intrinsic problems for modeling precipitation. From a mathematical point of view, precipitation observations can be understood as measures or quantities belonging to a metric space. These measures can be described by singularity exponents that explain how precipitation magnitudes change with the scale. Singularity exponents are associated to the fractal dimension of these measures. These fractal dimensions explain how the exceeding probability of precipitation change with the scale. So, scaling properties of precipitation help us to understand properties of its probability space. In this slide, we see a precipitation time series, one that was taken from the precipitation network of Mexico City. We can also see the decomposition of precipitation time series by classifying precipitation measures according to specific values of the singularity exponent. The higher the value of the singularity exponent, the smaller the value of the precipitation measures. The way these measures fill the space is quantified through their fractal dimension. For high values of the fractal dimensions, the embedding space becomes full of precipitation measures. Continuing the decomposition for all possible scaling exponents, we can obtain the multifractal spectrum of the precipitation time series. Here, the left plot exhibits the codimension function, and the right plot shows the fractal dimension function. These figures are multifractal spectra, and they both represent the same statistical structure of data, but from a different geometric point of view. Either the codimension function and the fractal function can also be estimated by analyzing the statistical moment of data. As mentioned before, the precipitation measures follow a power law with respect to the scale. Likewise, statistical moments also follow a power law with respect to the scale. But here, the exponents are no longer called singularity exponents, but moment scaling exponents. Let's now talk about one of the problems that encourages this research. This slide shows the spatial correlation function of 30 years of annual precipitation data located in some specific region of the north-central continental of the United States. If I take this picture for planning the design of a precipitation network, and I want to design a highly correlated precipitation network in this United States region, I would suggest to take at least a correlation length of 35 kilometers for getting a gauge density of almost 4,000 square kilometers per gauge. Applying the same technique for a set of observations recorded over the metropolitan area of Mexico City, the correlation-based estimation of the gauge density for this network determines that a wider number of rain gauges is necessary for a high correlated precipitation network. For instance, if one takes a correlation length of 3.26 kilometers, the gauge density would be 33 square kilometers per gauge. Although we have a less correlated precipitation network, the spatial coverage is not good enough for all the metropolitan and surrounding areas of Mexico City. This plot shows that there are spatial gaps to be solved by future administrations of the precipitation network for a better operation and security of the water system. Many regions in the world, as Mexico, exhibit inadequacy for measuring precipitation and other meteorological variables. Fortunately, we count on satellite and reanalysis products such as IMERS and CHIRPS. These products allow us to have gridded precipitation fields and information for climatological analysis. However, these kind of precipitation fields are recorded in coarse, spatial, or time scale. And some applications, as the design of water infrastructure, require high-resolution information. How can we take advantage of the coarse-scale precipitation products for applications that require high-resolution information? As mentioned before, we can take advantage of fractal theory, which deals with fragmentation processes in different scales. If one can identify a synergy between fractal theory and the statistical management of coarse-scale data, a powerful tool could emerge to solve several problems in meteorology, hydrology, and so on. This research developed an approach to get a solution as indicated before. With IMER and CHIRPS, we are dealing with two-dimensional precipitation measure that can be modeled by a multiplicative random cascade process. This is a scale transformation processes given by product of random variables. As with all models, we need to lie down in some assumptions. The main one is that the multiplicative random process is a canonical one. That means that the average value of the field is preserved in all the scales. There should be also restriction on the singularities to be modeled according to what is physically possible to get. In that sense, we have adopted that the largest singularities of the simulated precipitation fields are constrained to a statistic of point measurements over the study regions. Several studies have looked for a mathematical representation of the altitudinal variation of the precipitation, but there is not a unique mathematical representation because it seems to depend on regional conditions. For instance, in some regions, such as New Hampshire and Central Arizona, United States, there seems to be a linear relationship of the altitudinal variability of the precipitation. So in other regions, there seems to be an exponential relationship, but in tropical regions, or even subtropical regions too, there seems to be a rarer behavior in the altitudinal variability of the precipitation. As part of the innovation of the introduced approach, the inclusion of a topographic precipitation enhancement function in the random cascade model allows us to model any kind of regions with complex topography. In general, simulated patterns with random cascade models present a problem known as blockiness or block shade problem. This problem is understood as blocks of precipitation over the space domain that seems to be unrealistic. The solution to this problem was solved by including a diffusive filter to improve the spatial structure of simulated precipitation patterns.
That's good.
Okay, so far we have gathered the essential element of this approach. Let's now illustrate some application of this model. As observed in this slide, there are 3 time series of average field values of the precipitation products and simulated precipitation fields. These 3 time series exhibit equivalent statistics. Moreover, the appearance of all 3 precipitation patterns is quite similar. So the main constraint of the 3TRC approach allows us to obtain a high-resolution precipitation field with a similar statistical structure of the coarse-scale precipitation product. The statistical structure of precipitation field is also characterized by the codimension function. The codimension function of simulated precipitation fields is quite alike to the codimension function of CHIRP's precipitation product. Clearly, there are intrinsic differences between CHIRP's and IMER precipitation products. IMER lays down an overestimation of low quantities that makes IMER richer in low-value singularities than those observed in CHIRP's. The topographic random cascade approach is also capable of representing the annual precipitation cycle and some other long-term statistics shown in this slide. Another important feature to highlight of the TRC approach is its capability to improve the spatial pattern structure of precipitation after the downscaling process. For instance, IMER precipitation product has a spatial scale of approximately 10 kilometers at this latitude, Mexico. Therefore, IMER precipitation fields are set forth by quasi-homogeneous patterns that they don't allow us to identify the effect of topography on the precipitation field. However, simulated precipitation fields with the TRC approach shows a better spatial description of precipitations in regions with complex topography. Let me end my presentation with some final remarks. Many regions in the world deal with the problem of restricted measuring or recording of precipitation data. Despite there could be many technical, social, economic reasons that do not allow us to improve the sampling of point observations, the Coarse-Scale precipitation products can provide us suitable data for understanding local dynamics as we do for Mexico City. Second, here we are not in possession of physical criteria to make possible the downscaling estimation of precipitation fields. But with a scaling property-based criteria, there is an alternative and suitable solution to the downscaling estimation. Finally, with this word, my colleagues and I want to set a precedent about how to deal with the problem of the lack of information in study regions. So we believe that the TRC approach can be extensively used in engaged regions. For further information about this work, you can contact us or make a review of the following papers. Thank you so much for your attention.
Great, thank you, Victor. So I'm looking at the Q&A. I don't see. Just just now, I see some questions for Vanessa, which she's addressing here. So that's great. If we have questions and answers that can't be addressed now, please use the Q&A. I find the approach really motivating. Can you comment a little bit about the scaling exponents across different representations? Are we expecting the scaling exponents to change as we represent precipitation differently in models and observations, or is that?
Okay, that is a very good question. Let me start from here. Okay, here. So in the motivation, I show that we can represent the precipitation observation as measured, and so those measures can be represented by scaling exponents, alpha or gamma E, that you can see in equation 2 or 3. The following slide shows a decomposition is something similar to what I do what we do when we have a Fourier transformation of any pattern. But in this case, it's just a fractal theory behind this decomposition. So in this time series, the decomposition provides us the possible scales that we can find in a time series. However, in models and other kind of simulation, the scalings are reduced. It's a short set of scales that the models can represent. So this kind of models is something better because can represent a wide variety of scaling exponents, and we can also represent events that they are not seen in data, in the original data from Coarse-Scale simulated data.
Great. Yeah, it is worth experimenting, I suppose, just to see how similar. But Thank you. That, I mean, it's really a neat topic. I think there's a lot going on that could be explored here, especially with precipitation and also in climate forecasts. I believe there's work going on at CMC. But yeah, let's leave that for the offline chat and go to the next speaker, who is thank you, Victor.
Thank you, Doctor.
Thanks. Rajesh Shrestha, speaking on streamflow simulations, and I'll let you take it over. We're a bit behind, so but I don't think we need to worry too much. So carry on, Rajesh, if you can, please. You can, yeah, there we go.
Can you hear me? Good.
Yeah, you just have to go to the presentation mode. Yeah, thanks. That's great.
Yeah, slow here.
It's okay.
Yeah.
Well, hold
Hello,
on. We're seeing online. We're seeing your view, which would be the next slide with notes. Is there maybe another way to?
Okay. So I don't know. Maybe I should stop sharing and try
Stop sharing.
again.
Yeah.
Yeah. I'm not so sure. But maybe I'll just stick with the here. I don't know. Try sharing again one more time.
Yeah. It might depend on what you share. If you share your whole screen or just the presentation, but whichever you did, maybe try the other way and see. We're seeing it here. That's good.
It's good now?
Just go to presentation. We'll see if that works. Yeah, we're seeing the same view, which is your view.
Okay. Yeah.
No. Okay.
Okay.
Thanks, Colin. That's great.
Good.
Thanks.
Thanks for that. And yeah, sorry about that. So yeah, my name is Rajesh Shrestha. I'm from Environmental Climate Change Canada, and I'm presenting today on streamflow extreme changes in subarctic river basin in Canada. This is a part of a larger study that we are undertaking, looking at future hydrologic changes across Canada using a multi-modal ensemble approach, in which we are using a multi-hydrologic model to project different components of hydrologic cycle. Before going any further, I would like to acknowledge contributions of my collaborators or co-authors, who are Alex Cannon, Spiros Belteos, and Laurent Diram, all from Environment and Climate Change Canada. The warming climate is leading to intensification of the global water cycle as a result of changes of moisture fluxes between land surface and atmosphere. In this respect, very relevant to northern Canada is enhanced warming and amplified moisture transport to the north, related to Arctic amplification or polar amplification, because this changes in north, large-scale changes in north, can affect different components of the hydrological cycle, like snow, seasonal stream flow and extremes, and may lead to larger flood events. However, there's limited knowledge in terms of how flood extremes will change across different parts of Canada in general, and in particularly in the northern Canada, where we have very, very few studies. And unlike climate modeling, we also don't have consistent set of future projections across the country. So with that in mind, our objective in this study or in this project was to evaluate future changes in hydrologic extremes across Canada in relation to different drivers. For example, in a recent study that we undertook, we looked at future changes in snowpack compared to changes in winter temperature and precipitation. So for example, at the 3 degrees global warming level, we see decrease in the snowpack in southern parts of the Western Canada region, and slight increase in the northern part. But it is not entirely clear how these changes will affect streamflow extremes in different parts of the country. Further complicating the matter, especially in northern Canada, is the presence of ice in the river. As you can see here, when there's ice in the river, we see quite a large difference between difference in water level. This is from our gaze in Mackenzie River Basin. We can see that compared to the open water period where we don't have river ice, the peak water level under ice conditions can be 5 to 10 meters higher. So this can cause a large difference in flooding when there's ice in the river. A graphic by Benoit Turcotte from Yukon University provide a very nice illustration of how river ice breakup occur. So he kind of illustrated different forces and mechanisms that drives river ice breakup and flooding. And he suggested that ice cover acts as a resistance, and discharge on the ice cover acts as a driving force. So how river breakup will occur and how flooding will occur will depend on the interactions of different variables, ice cover, discharge, and other variables that will affect the ice cover and ice melt. So for this presentation, I'll focus on the Liard River Basin, which is a large river basin in the Mackenzie River, and it covers about 16% of basin area and contributes about 25% of discharge to the Mackenzie River. The basin is mostly in very pristine state, so that meaning that it's not affected by human impacts like regulation and water withdrawals. So it makes also a little bit simpler to analyze future hydrologic changes compared to other basins which are heavily regulated. So for this basin, we have a hydrologic model set up. It's called a Vic hydrologic model. It was set up at 1/16 degree resolution. We calibrated model for 30 sub-basins within this Liard River Basin, but I'll focus mostly on the results from the at the outlet of the basin. The big model has been very widely used in this part of the region. It has different components necessary for cold climates. For example, it has a good snow algorithm, uses full energy balance, and it also has a frozen soil algorithm, which is very important to simulate streamflow changes in these kind of regions. So going on to the future hydrologic projection framework, we use an ensemble of 8 global climate models for 2 shared socioeconomic pathways, SSP 245 and 585. Those 8 GCMs are selected based on a study by Mahoney et al. In 2022. We use a statistical downscaling approach developed by my co-author, Alex Cannon, called n-dimensional multivariate bias correction algorithm. A good thing about this algorithm is that it preserves multivariate dependencies between different variables, for example, temperature and precipitation, which is very important for regions like Canada, because snowpack depends on the interaction between temperature and precipitation. So if we are able to have those two variables dependencies correctly represented, then there's a better simulation compared to the ones which use a single variate bias correction. As I said, we are using a Vic hydrologic model, which is a version 5 developed by University of Washington, and it has been widely used for future hydrologic projects in different parts of the country. And we have used this for Liard Basin for other purposes as well. So we are based on the driving DCMs, we are projecting different components of hydrologic cycle using the weak hydrologic model projections. So, for example, stream flow, snow, soil moisture, evaporation, etc. But I will focus on only the stream flow in this presentation. And then we are looking the projections at global warming levels from 1.5 degrees to 4 degrees compared to the pre-industrial period of 1850 to 1900. And looking at the extreme events, we are looking at both the extreme events under open water and ice-covered conditions. And we are using a GV distribution for flood frequency analysis. There's not a simple way to estimate ice cover using a weak hydrologic model because it doesn't have a river ice model within it. So we are using a simple approach based on flow duration, flow lag from the first initiation as suggested by Kaya in 2001. And for the estimation of ice cover thickness, we are using an approach developed by my co-author, Spiros Beltoyos, in the recent study for the Peace Athabasca River Basin, where he modified the Stefan equation for the simulation of river ice thickness and projections of future changes in river ice thickness. It's a simple method, seems to be pretty effective for what he has done, and it estimates river ice thickness based on total winter snowfall and accumulated degree day of frost. So going on to the results, these are the results for mean temperature and precipitation changes. 4 colors here represent for global warming levels, 1.5 to 4 degrees. And the black dots represent the median of the ensemble. And as you can see here, mean temperature is changing for all seasons and increasing with the global warming levels. It's also interesting to note that the mean temperature changes are higher than global warming levels. For example, at 4 degrees global warming level, we see more than 6 degrees of change at the local basin level, which is to be expected because this Liard Basin is located in subarctic region where we see the effect of larger temperature increase. Precipitation is also projected to increase across all seasons. They're quite consistent. There's not much difference between seasons. Maybe a little bit less in the July, August, September compared to other seasons, but we see temperature increasing consistently and also increasing with the global warming level. So we see higher temperature increase in all seasons with higher global warming levels. Looking at the results of maximum and airfield first snow water equivalent, we see very little change for this basin. This is the basin average value of snow water equivalent. So compared to the historical period, they are very similar, maybe a little bit decline at 4 degrees of global warming, but they are very consistent. So this may be a little counterintuitive to see that snows remain constant or consistent with the warming temperature. But Liard Basin being in north will remain cold even with higher level of warming, for example, 4 degrees of warming. So, and also there is an increase in precipitation. So those two factors will compensate the temperature-driven decline in snow, and so we'll have consistent set of consistent snow, even though temperature is increasing.
In a few minutes.
Thank you. So mean and maximum flow changes across the basin. We see changes very similar for both for mean and maximum flow. Maybe a little bit less. The increase in the July, August, September, we see decrease, but all other seasons so increases. And July, September is interesting because we see increase in precipitation in those seasons. So this has to do with the two factors. First, increased evaporation during that season, and also shift in the timing of the peak flow to earlier months, which will also reduce the flow in this season. So we see similar results for both maximum and mean flow. Looking at the annual maximum flow flood frequencies, we see that decrease in return period with respect to any specific flood discharge event. For example, for annual maximum flow, 100-year flow will become about 20-year flow at 1.5 degrees global warming, and about 5-year flow at 3 degrees of global warming. So implications of that on river ice breakup. So we see that using the simple approach that we are using, maximum ice thickness is projected to decrease progressively with the higher level of global warming. So this will have implications on river ice breakup flooding, which we need to investigate, because thinner ice cover means that there's less resistance to breakup, and then there's a higher driving force because of higher discharge. So we don't have the projections of the river ice breakup flooding, but looking at the historical period, we see that peak ice influence discharge is increasing, peak ice thickness is decreasing, and peak water level trend is increasing. So it appears that discharge is driving the increase in the peak water level. I'll stop here with my summary and future work, and then I'll be happy to take questions.
Okay, thanks, Raj. Great. Let's try to put some questions in the chat if we can. You've taken away with those last slides. You took away the historical trends that you already show are occurring, and you can explain them. So yeah, I don't have that. That was my question, but thank you.
Yeah, I can share back. Yeah, I can do that. Yeah. Yeah.
Okay, so yeah, I could text as well in the chat. And meanwhile, Alex Sabe is going to segue into the lake ice and then snow topics. So how would you like to go? Do you want a reminder after both of them are done, or do you want to split them up?
I can just split them up because they are somewhat different topics, and that's how I was planning. So,
all right, I'll give you a reminder at 10 minutes then.
Sure thing. Thank you. All right. So is my screen share all clear?
Yeah, that's good.
Okay. So thank you very much for having me in this session. I was not intending to have 2 talks in the same session, but I think one I signed up for got canceled. So in any case, though, what I'll be talking about for this talk is modeling Northern Hemisphere lake ice phenology using the Canadian lake ice model. And so this is, so I'm Alex Sabai. I'm from UTM, Department of Geography, Geomatics, and Environment. And this is work I'm doing supervised by Dr. Laura Brown. So first, just some background on lake ice and why we're interested in it. Now, Canada has access to approximately 20% of the world's freshwater, much of which is contained in lakes. Frozen lakes, particularly in northern regions, are often used for fishing and transportation. Arctic lakes are often in particularly remote regions. They're logistically challenging to observe in situ. An example showcasing this is the image on the left, which is from a field campaign we had last month, where we flew in on a twin otter to Laura Lake on Cornwallis Island. And we took some measurements and also took care of some cameras that we had set up there. So in addition to in situ measurements, there are also remote sensing measurements that are available, but those have some limitations with periods of instrument operation and may be difficult to discern breakup and freeze up. I had a presentation earlier this week that discussed that more. But now for another approach, however, In this work, I'll be talking about modeling the Northern Hemisphere lake ice cover using the Canadian Lake Ice Model, or CLIMO for short. So some brief notes on what CLIMO is, the Canadian Lake Ice Model. This is a thermodynamic lake ice model, single column, so no horizontal coupling. It basically just looks at inputs from air temperature, relative humidity, wind speed, and cloud amount, and through looking at the energy transfer through the surface of the lake ice and through the water surface, you get thermodynamic growth of lake ice, depending also on radiative properties, which you get from the cloud amount. Optionally, also, you can include snow accumulation and density, which then accounts for the insulation factor from the snow onto the lake ice surface. That work is still currently in progress, but I'll be talking about some work we've done in that as well. The outputs from CLIMO we get are daily lake ice thickness, as well as specific freeze up and break ice dates that are calculated based on the ice crossing a very low thickness threshold to essentially consider when there's no days of no ice versus when there are days of ice. The current run that I'll be talking about in this work is a run driven with meteorological input from the ERA5 land reanalysis product, years 1980 to 2020 and 0.25 degree resolution. And this will be over the entire Northern Hemisphere. Just another thing to note with CLIMO finally is that it can be run for different lake mixing depths. The runs that we've done are currently 3 meters, 10 meters, and 30 meters. So I'll just be showing some samples for the entire hemisphere. But if you were interested in a specific lake, you could choose a mixing depth that was better suited to that particular lake. So now, working with CLIMO, it provides breakup and freeze up, but there may be multiple breakup and freeze up dates per season. And so to identify when the breakup and freeze up are for each given season, I developed a detection process where first we aggregate the freeze up and breakup dates, and then for each season, I find the longest freeze up breakup interval. So the longest period of continuous lake ice cover for each individual grid point. Or sorry, for each individual grid point for each year. And then I record those freeze up and breakup dates as the freeze up and breakup for that season. There are a few caveats with this approach, which we're still ironing out. Particularly, some regions experience multiple freezing periods of similar length in some seasons, or sometimes you get regions that just have persistent ice cover for multiple years, which can make it a bit more difficult to discern. But this approach is suitable for most regions. This work is still being currently under development, so some of the results I'll show will have some caveats. But again, this will just give you a general idea of what we're working on. So without further ado, then here are some sample output for an early year of freeze up and breakup in the no snow run of 10-meter mixing depth. So the year of 1980. And so here we can see when the freeze up and when the breakup are happening as a day of year. When the freeze up is greater than 365, what that just means is that freeze up occurred after January 1st. So what we see here is that, kind of as expected, in colder regions, we tend to see a earlier freeze up as well as a later breakup. In sort of the very northern parts of the Canadian Arctic archipelago, you see that there's no freeze up or breakup date because those are actually regions where there was continuous lake ice cover during this year. And conversely, of course, in more southern regions, you do see that there's freeze up happening later and breakup happening earlier. But also you can see that there is some variation that's partly seems to be associated with topography, for example, in the Rocky Mountain area, where you can see that there's somewhat the ice is persisting somewhat longer in the higher altitude lakes. So overall, it tends to track temperature quite well. Now, for comparison, we can see a later year of freeze up and breakup. So immediate thing that kind of sticks out the most is now you have parts of the world, for example, if you look at Europe or at kind of the United States area, you can see that there's now regions where we're not getting any freeze up or breakup happening at all anymore. And so that's a key difference, that some lakes from year to year by region, it may vary, but in general, you're seeing more regions where lakes are not freezing and breaking up at all. Also in the very northern regions, you may now see that some regions that previously hadn't been experiencing breakup are now experiencing breakup. So that's just to highlight kind of differences between the beginning and the end of the time series. We can also look at decadal differences to get kind of a more general picture that isn't so influenced by year-to-year variations. And so what we see here is that for the 2010s minus the 1980s decadal difference, if we're just looking at the freeze up, we're seeing in general that there's freeze up happening later in later decades. Again, that's kind of consistent with what we expect given climate change and so on. Note that the scale here is a bit cut off just so we can see some of the smaller variations in freeze up date. But nevertheless, we can see particularly in the northeastern Europe area, there's quite later freeze up. One thing to note is that there may be some artifacting happening kind of in the western US region where there's quite a lot of regions where freeze up may only be happening in some areas at certain times. So because of that, it's kind of more grainy. We may need to do a bit more QA to look at the sampling there. But the overall picture is that we're getting generally later freeze up. There is some earlier freeze up in southwestern Asia and slightly in continental North America as well. Now for the changes in breakup between decades, we're seeing also, again, earlier breakup in most regions, especially in Eastern Europe and also Northern Siberia, you get much earlier breakup. And also, there's a little bit later breakup in, again, this kind of central Canada and northern US region, kind of in the prairies. So we're still working on investigating, what are the driving factors of this, but nevertheless, it's kind of an interesting result to consider. So now, these were all from model output of CLIMO run without snow cover on the lakes. So now, currently kind of in progress is work we're doing with running CLIMO with snow input, also from ERA 5 land. So the key caveat here is that ERA 5 land by itself does not produce snow depth or density over lake ice. You can see this in the upper left panel where that is snow depth taken directly from ERA 5 land over Great Bear and Great Slave lakes. And you can see that the lake grid points are just completely free of snow. And this is true for, all of the years. The model the reanalysis product just doesn't include snow over lake ice. So to kind of account for this, what we did was we linearly interpolated snow from adjacent regions around the lakes onto the lakes themselves. We use a threshold of lake fraction greater than 0.2 just to make sure that the grid points were thoroughly snow covered. And the result that we get from this regridding is shown on the bottom left panel. Note that this is shown at a 0.1 degree resolution. We regridded it to 0.25 degrees for the CLIMO run because that's what we're running CLIMO at the moment. But so that smooths out some of the sort of artifact we get here. But generally to get it, it gives a sort of broad sense of what the snow depth is. And based on consulting we did with some land snow colleagues, this is a reasonable approach given what we have available. So again, as I mentioned, running CLIMO with snow is currently in progress, but here's just an example of a single grid point comparison over Eleanor Lake over Cornwallis Island, shown on the map on the right here, just to give you an idea of how this actually impacts the lake ice. And so what we see is that when we run CLIMO with snow, we end up getting freeze up happening later than if we run it without snow. And conversely, we end up getting earlier breakup. This is largely attributable to the insulating properties of snow. Even during the freeze up season, snow will fall quite readily in this region over lake ice, and snow inhibits the growth of lake ice. So overall, we end up getting a thinner lake ice cover as well. And so because of that, when the ice is thinner, it'll end up melting away earlier as well. So those are the impacts that we're finding for adding snow in this region. Again, we're going to do some more investigation of how that impacts the hemisphere as a whole. But just for reference, that's what we're finding so far.
That's 11 minutes.
All right, good timing, because here's my conclusion slide. So in conclusion, again, ongoing work, but we find freeze up in later and later decades for most regions, particularly Northeastern Europe. Breakups happening earlier in most regions for later decades, except in Central North America. And our next steps are going to be running CLIMO for the entire Northern Hemisphere with snow from Era 5 land. Now, note, we have actually done this. We're just in the process of aggregating the data and processing it to be plottable, I suppose. Furthermore, additional observational validation and statistical analysis. We do have some in situ measurements available from some of our observation sites. And finally, we'd use CMIP6 input to CLIMO to run future projections of lake ice under various scenarios. So that's all for this talk of mine.
Super. Thanks, Alex.
Thank you.
Okay. I don't see any questions yet. So a quick question is, given that these are offline simulations, but that I mean, snow cover is part of a coupled feedback in the climate system. So
yes,
how would you address or expect things to change in a coupled context?
Oh, that's a very good question. I mean, we'd expect there to be some sort of feedback in terms of, well, for example, you've just an albedo feedback with snow cover enhancing albedo, and thus there'd be less, less maybe localized warming. But conversely, you may have competing factors from the fact that the snow cover does also insulate the lakes from the atmosphere. So on the scale of smaller lakes, I suppose it may not have as strong of an effect, but for larger lakes, you may see more of an impact. But either way, that's a good question, and I'm sure there's other things to consider that I haven't mentioned as well.
Yeah. Okay. Yeah. So yeah, I'll let you go ahead with the next talk since you're all sped up, and I'll give you another. You have an extra minute or so you can take your time on this one if you want.
All right, made up the time that I had there.
Yeah.
Okay, so now in contrast, previously I was talking about lake ice, but here now I'll be talking about assessing the impact of differing snow inputs to reanalysis-based snow on sea ice reconstructions. So again, we have a model we're using reanalysis input to it, but some of the details here are a bit different. This is work that I did as part of my PhD under the supervision of Paul Kushner and in collaboration with Alec Petty, who's been very instrumental to this work. So some background on why we're interested in snow on Arctic sea ice. It's implicated in a variety of climate processes, such as the ice albedo feedback. It moderates atmosphere ice ocean heat fluxes. It can also contribute to the ocean freshwater budget. In addition, I have this little picture of a seal here because it actually has a biological impact in that ringed seals make their habitat on snow on sea ice, and they need at least 20 centimeters of snow to be able to make their dens. Snow has many complex processes with differing seasonality and regional characteristics, as you can see illustrated in this illustration here. So it can be quite difficult to represent. Nevertheless, it is required for the production of altimetry-based estimates of sea ice thickness, but it's quite challenging to observe due to the remoteness of Arctic sea ice. And so one approach that has been used to produce estimates of snow on sea ice is using reanalysis-based snow on sea ice reconstructions. Namely, some examples of them that I'll be talking about here include Nisosim, which I've worked with a bunch, and then there's Snow Model LG, which, to be clear, Snow Model LG I did not run. I'm using available model output data, but it'll be used as a point of comparison. So more on Nisosim, since that's the model that I've worked with and contributed to. This is the NASA Eulerian snow on sea ice model. It is a very simple model. There's 2 layers, 100 by 100 kilometer grid squares, and each layer has a prescribed snow density, and then there's a few simple snow processes that act on the snow in these layers. It takes snowfall input from reanalyses scaled to satellite observations, and one key thing to note that I'll be discussing a bit here is that there's 2 free parameters. There's the blowing snow parameter, which governs the strength of loss to the atmosphere and to open water, depending on wind speed. So snow is being blown off the sea ice. And then there's the wind packing parameter, which governs the snow density in the model. Again, there's just 2 prescribed densities in each layer, but the snow density is represented as a height-weighted average of the two densities, and the amount of snow that's transferred between layers is governed by the wind speed multiplied by this wind packing factor. So these parameters in my previous work were calibrated to observations, well, calibrated by calibrating the model to observations of snow depth and density using a Markov chain Monte Carlo method. And so I'll discuss a bit of what I've been doing there. I won't go into too much detail of the intricacies of Markov chain Monte Carlo. I have a publication on that if anyone wants further detail. But the gist is basically we calibrate the model parameters by comparing the model to observations and find parameters to give the optimal match between the output and the obs. And then we obtain optimal parameter distributions. So the observations we used were airborne and in situ snow depth and in situ snow density measurements. The previous calibration work that I did, we ran Nisosim with ERA5 snow input and calibrated the parameters. But now the current work that I've been doing has this parameter calibration repeated when you run Nisosim with different snowfall inputs. So we have snowfall input from ERA5, JRA55, and MERA2 reanalyses. And on the right, what you see is a plot of the posterior distribution. So distributions of the parameter values that are obtained when the model is calibrated with these three reanalysis inputs, two observations. And so we can see that depending on which input we use, we actually get different optimal values of these parameters. So there's some tuning that's been happening with this model. Previously, this was manually done. So one of the assets of this approach is that it's done automatically. Now, what does this actually look like in terms of the output it produces? On the left two columns, we have snow depth and density climatologies, which are done with only one set of parameters being used for all the products. Blend denotes the interproduct average here. And after, on the right, we have Nisosim output after each individual calibration has been done. So what we see is that for the upper row for snow depth, the climatologies are reconciled. There's a smaller difference between them once we run this calibration. However, with the densities on the lower row, we actually see that there's a wider spread of the densities when we use the individually calibrated values. Now, the reason for this we expect is because there's much fewer observational constraints on density than on depth, and density is more sensitive to parameter values and to snow input, since it's primarily just a function of how much snow is in each layer. Nevertheless, for the application that we are considering for sea ice thickness, it's more sensitive to depth and density, so we proceed with the calibrated parameter values. So now to further investigate how this calibration looks, and also how using different reanalysis input can affect snow model output, we are doing a regional comparison with snow model LG. This is a Lagrangian snow on sea ice model, so it's actually tracing sea ice parcels as the season evolves. It includes more detailed representations of snow processes than Nisosim, but it's considerably more computationally expensive to run. However, it is at a higher resolution. And so snow model was run with ERA5 and MERA2. And again, we did not run this model, but we got the output from the NSIDC. The different regions that we're looking at, there's a schematic map here from March 2023, which shows them. They're selected based on differing sea ice characteristics in the region. For the purpose of this presentation, I'm just going to show a selection of the regions listed below on the slide, just for the purpose of making it easier to see the differences between the regions. But they're relatively representative of different parts of the Arctic Ocean. So without further ado, now there'll be a lot of output here, so I'll just try to focus on some of the main points, but I'm happy to discuss finer intricacies later on. First off, regional climatologies for the snow depth. We see good agreement overall on the Central Arctic, the Beaufort Sea, and the Chukchi Sea. Snow model LG, which you can see denoted by the dotted lines here in the blue and green, it has a low end of season bias in the Beaufort and Chukchi regions. We assume, or we think that this is likely due to the fact that snow model includes melt processes, whereas Nisosim doesn't. And we do expect melt to be acting to reduce snow depth on sea ice at this time. And then in the Kara Sea, the Barents Sea, and particularly in the East Greenland Sea, what we see is that there's less model in snow model LG than Nisosim. It's hard to say which one has a better representation because there's a very limited number of observations or validation, but we can just see that there's relative biases between the two models, regardless of which snow inputs are used. Now, looking at the snow density, we can see that compared to the snow depth comparison, there's less agreement in snow density. This is partly just because Nisosim snow density is constrained to less than 350 kilograms per cubic meter. So in every region, Nisosim snow density basically increases until about the maximum density, and then it kind of falls off. This is just a limitation of the model itself. So as a result, because snow model has a more complicated representation of density, it allows for some snow metamorphosis. There are more differences between the regions in the seasonal cycle. One key thing to take away, however, is that the density biases do not necessarily compensate for the depth biases between the models. For example, in the East Greenland Sea, we do see that snow model has a lower depth and a correspondingly higher density, suggesting that the higher density may account for some of this difference compared to Nisosim. However, in the Kara Sea, snow model has a lower depth overall, but it still has a lower density as well relative to Nisosim. So when we're talking about biases between the models, density differences are not the full picture. Now, snow volume and ice area, I'm showing these simultaneously just because they're kind of tied together. Briefly, the snow volume interproduct biases generally resemble those for snow depth, with this large difference between Nisosim and snow model in East Greenland in particular. Low early season snow volume is associated with low ice area, as is kind of expected since they're directly dependent on each other. So in the Central Arctic, where you do have a relatively large early season ice area, you also see a larger early season snow volume. Higher latitude regions, more central regions tend to become fully ice covered toward April. That's what you see if you look at the sea ice area on the bottom in the Beaufort and Chukchi seas, for example. They're fully ice covered from November or January in the case of Chukchi Sea. And so the shading here represents interannual variability, and you really don't see that toward the later months because it just ends up fully ice covered. Conversely, in Barents and East Greenland, because these regions don't end up fully ice covered, you see quite a large amount of interannual variability, which may contribute to some of the volume variability there. So now, those were climatology plots. Now just looking at trends, I have the same layout here, so I'm showing two at once just to kind of intercompare.
That's 10 minutes.
So, thank you. So the inter-input differences in this case are larger than inter-model differences in some regions for snow depth. That's kind of one of the key points. If you look at the Central Arctic here, you'll see that snow model and Nisosim driven by MERA2, the green lines are actually quite close to each other, and they show a significant decline compared to those same models driven by ERA5, which are in blue, where the significance shading overlaps with 0. So depending on which reanalysis input you use, you may actually get different conclusions about the strength and the significance of the trends. So that's just kind of tying into a general caution when working with reanalysis products, where trends from reanalysis products may be somewhat dependent on products being assimilated. You see significant depth declines towards end of season for all products in Chukchi, Kara, and Barents. Density results need to be interpreted with caution because due to the model density representation being limited, its variability is also limited. But we see slight declines in most regions of density overall, more in snow model LG. Except in East Greenland, where for both snow depth and density, there's generally not statistically significant trends. And this region is just highly variable overall. So we don't see that so much. Finally, snow volume and sea ice trends now to complete the picture here. In the Kara and Chukchi Sea regions in particular, we see this strong decline throughout all months except for September. This may be associated with the early mid-season sea ice decline, which we see in the sea ice area. Other studies have found similar results. And furthermore, we see a significant end-of-season volume decline in the Barents and East Greenland seas, which In particular, in East Greenland, the snow depth doesn't show much of a decline, but the volume, particularly in the mid to late season, shows a strong and significant decline for both the SOSM and snow model. So some of that is likely associated with the ice area decline. All right, so just some brief conclusions. Snow depth and density measurements can be used to calibrate the SOSM model parameters when you use different snowfall inputs. We do see an improved agreement in depth after this calibration between products, but decreased agreement in density. There are various regional variations in snow climatologies and trends. Agreement with snow model varies by region. Early season sea ice area decline can be associated with later season snow depth decline in some regions, consistent with other work. And some regions with no significant snow depth trend may show declines in snow volume associated with a sea ice decline. That's all for this. Thank you.
Great. Okay, thanks, Alice. Again, I was searching. Maybe I'm not searching the right place. So if there are any questions that do pop up after, we're heading towards a break now, but I guess and we'll come back. I think if there aren't, I don't see any questions, so I'll ask one. In terms of, was it a Bayesian method, the MCMC method?
Yes.
And in general, as a general question, would there be any is there a strict adherence between the model and OBS comparisons, such that you want strictly to make the model look like the OBS, carte blanche, like without any clarification, without any qualification there, or does the model somehow allow for there to be differences between the two if there were some reasonable reasons for that to occur?
Yes, that's a good question. I didn't go into the details of the method, but it's a maximum likelihood optimization. So it does allow for some uncertainty in the observations. Mm-hmm. So, and we do account for that with the observations we use. We include some uncertainty factors there. So it's not necessarily matching exactly, but there is some wiggle room.
Okay. Very good answer. Okay, thanks.
Thank you.
All right. So yeah, we have a few minutes to break, and then our session begins again. So thanks to all the speakers, and yeah, please join us on the back end of this session. Thanks, everyone.